Hello, welcome to another episode of Baz Codes. I'm your host. Uh, Let me get back to you on that. After my last video, I went back and forth with some folks on the old face space, and someone posted a old basic benchmark, and I was curious to try out and see how that worked on GS squared. And anyway, uh, my emulator ran it almost 10% faster than it should have. So after doing a little thinking, I double checked some of the, simulation of frame timing and whatnot. I decided that was okay. So that left as a possible culprit that some of my CPU instructions weren't actually ticking off as many cycles as they should have, essentially running faster, seemingly running faster than they should have. I used the GSSquared debugger to identify that basic program was doing tons and tons of rotate left, comma, X instructions off the 0 page. I'm guessing that was all floating point stuff it was doing, since there's tons of floating point going on in that the little test program. And indeed, I looked at the debug output, and those instructions were only taking 4 cycles, and they should have been taking 6. So that led me down the rabbit hole to I tweaked those and got those correct, but then it occurred to me that I probably should just test all of them. So I wrote a test harness for my CPU library, CPU module for the 6502, and put it together along with a little routine that basically executes every possible variation of a 6502 instruction in terms of the different instructions and different addressing modes. And then there's cases where the same instruction will take an extra cycle, if it wraps around a page boundary and things like that. So anyway, I did all that, and here we are. So I set up the test program. I didn't show that in the video, but then I went through and actually used the test program and the results out of it to help find and fix other instructions that weren't taking the correct number of cycles. So here is that. Enjoy. All right, so I've got indirect comma X off the 0 page seems to be a common problem. Let's do that. Okay, they're all reporting cycle too short. So, oh look, here I am. Okay, get operand address indirect X. So I need to add a cycle here because it is not. Where's my 6502 reference here? Okay. Indirect comma X is supposed to be just 6 cycles. Groovy. All right, so I've gotten the operand, sorry, the opcode, and then I'm reading the operand, so that's 2 cycles. And then I'm reading a word from the target of the operand. That's 3 and 4. And then I need one to add the X, and then one to do the add. So that's going to be 6 cycles. So I think I just need to add that here. Right. 12 failed tests now. Oh. And all of these passed with 6 cycles. Cool. Okay. Let's do this. Let's look at just the ones that failed. Break. That should be easy. Okay. So here's the this. So break is supposed to be 7, but I'm doing 8. Okay, so I'm pulling the opcode, that's 1. We're pushing this program counter, that's 2 and 3. We're pushing the processor status, that's 4. We're reading the break vector, that's 5 and 6. And then there's just supposed to be one more. So why am I getting, where am I getting 8 from? Oh, let's look at this. Okay. Oh, wait, what? Aha. This is not right. Because write byte is here. It doesn't increment cycles. Yep. So I'm doing a write and a write, and then this is here inexplicably. Let's disable that. All right. And then see what happens. Now, push word is probably used from some other places here. It's used, in the interrupt handler. And it's used in break, and it's used, for JSR. Interesting. All right. Let's see what we've got here. So I had 12 errors before. Now I have I have 12 errors again. Did I not? Oh, okay. Break is not on here. But JSR is now wrong. That's interesting. Yeah, right. Okay. So JSR is going to be the opcode. It's going to be 2 bytes of the operand. That's this. Let's go look at that. This is used all over the place. No. Wait, what? Oh, no, that's not relevant. Okay, get operand address. Absolute. I'm just doing a read word from PC, which is doing 2 read bytes. Okay, so that's fine. Get operand address absolute. That's here. Let's go back to the JSR. Okay. So the JSR is a cycle short. So it's opcode, operand. We've got to push the current program counter on the stack, which is this. That's what we just changed. And then it's just an extra one? Maybe we need a cycle to load what we fetched into the program counter. You can see how this is me doing a lot of thinking about how the 6502 actually moves stuff around inside its block diagram. And I'm deducing a lot of this as opposed to going from a definitive source of information. There's lots of stuff on the internet, and I'm sure if I dug into it, I could, look at the block diagram like so and figure out that there's this step that needs to occur. After we load this 16-bit value from memory, we need to push it into the program counter. And that could be a whole separate cycle for whatever reason. But that seems likely. Okay, well, I don't know how many that was. Let's see. Failed to tests 11. Cool. Okay, so JSR is off there now. Yep. So what have we got? We've got a bunch of arithmetic stuff. ABS, X. So let's go take a look at that. Let's start with, let's see, ASL, absolute, X. Okay. So the key, a key difference here with these things is that these are doing a read, modify, write to memory, right? So it's got to, if you're going to shift the value in memory, you've got to load it, shift it, and then write it back out. And that is common with all of these. Decrement, increment is going to be the same. So let's see what we've got here. Okay, so ASL absolute, X is going to be always 7 cycles. And we've got the opcode, the operand, 2 bytes of operand, so that's 3 cycles. We've got to read the current value, so that's 4. We've got to shift it, that's 5. We've got to write it, that's 6. And we've got to add the X, that's 7. Okay. So actually, I've got STA absolute, X here as well is a cycle too short. So let's go here and look at operand absolute, address absolute X. Get operand address absolute X. Read word from PC. We've checked that's 2 cycles. Well, that's interesting. So this is saying if we cross a page boundary, we add an extra cycle, but I'm wondering, this says that doesn't apply here. Let me look for all the absolute, X's. Okay, compare. Oh. So when we're doing a read, modify, write type operation, it always takes the extra cycle. if we're just pulling something in, if we're just doing a read and then, modifying a register or whatever, you essentially sometimes save a cycle. So that's really what it is. If it's the same page, we sometimes save a cycle, unless we're doing a read, modify, write. Well, that's going to be interesting to deal with here. Okay, well, I'm going to have to do it like this. I'm going to have to make a special version of this function for read, modify, write that always uses the cycle. And I'm going to have to use this version in places like this. So ASL, ABS, comma, X. We're going to do that. Okay, decrement, ABS, comma, X. Oops. This may not be needed. It's only used the one place. Sometimes when you're writing code, there's a way of thinking, which is to say, don't break things into a function until you've tried to use it twice. Going through this, I had a lot of stuff that I thought I would use more than once, but ended up not. So this is one example, but that's fine. Okay, so we're doing the X. We're in decrement, absolute X, read, modify, write. Let's go back. Decrement, increment, absolute, comma, X. Yeah, probably the same thing here. Yep. Okay. Now we're cooking with gas. Let's see. Oh, that's not an instruction we're interested in right now. Rotate left absolute, comma, X. Okay, thank you, AI autocomplete. That is correct. Okay, rotate right. Absolute, comma, X. Yep. So I did 1, 2, 3, 4, 5. Okay, now this, let's see. Stay. It's technically not when we're doing a read, modify, write. It's technically doing it when we are doing a write, isn't it? Because this is an STA, and STA doesn't read, modify, write. It just writes. So it is just 6 cycles. Store operand absolute X. I could rename this later to just be like get operand address absolute X in a write or something like that. That's fine. Okay, and then STA absolute, comma, Y is the same. We'll come back to that. All right, so we may have fixed 6 instructions here. Let's compile, see what happened. There's always the possibility that, I'll make a change and it'll break something. And that's one of the big benefits of using the testing regime here, right? 5 failed tests. Yeah. We're getting there. We're making some progress here. Okay, so what have I got left? Okay, load y from 0 page, comma, or sorry, load x from 0 page, comma, y. Okay, so this says load x from 0 page, comma, y. Should just always be 4 cycles. Huh. Load x 0 page y. So I'm doing get operand 0 page y. Okay, so I've got the opcode, 0 page, so there's only one operand byte, that's 2. We're looking for 4 cycles here. 4 cycles. And then the read byte, so that's 3. But when we're doing LDX indexed with y, we're using an extra cycle somewhere. That's interesting. So LDX 0 page, comma, y. Well, it acts like it's an absolute, comma, y. Probably because, I don't know, we got to go back into the x or something. I could just because that's the only. Oh, sorry, STX 0 page, comma, y has the same issue. Well, that's fascinating. I have this, but then I don't do it the same way here. I have store operand page y. Well, oh yeah, because on a store you don't change any of the flags. Okay. So that's actually sort of the same setup there. All right, so that's these 2 instructions here. Now, I'm going to make notes here and say, look into this and see where the extra cycle might need to actually go. Because if we're trying to be really specifically correct, right, we've got this extra cycle that creeps in somewhere when we're adding the X. It probably actually goes in before the memory read, right? And if we were, it probably wouldn't matter for most things, but let's say that this instruction, well, this couldn't, but let's say that somehow this instruction could hit a soft switch, right? If the read comes one cycle later, because we stuck this extra cycle in, I'm sorry, earlier, because we stuck the extra cycle in after the read, like we're doing here, then that I/O read could be in the wrong position. Now, in an Apple II, practically speaking, these are zero page. There's no I/O that's referenceable from zero page. But if we ever want to use this CPU module, like in a different emulator, you could, in theory, have I/O in some other some other computer. You could have I/O at 100. Who knows? So that is that. I guess that would be the stack. So practically speaking, you wouldn't. Anyway, you know what I'm saying. Okay, so let's build, and we'll come back to it. I don't want to sit here and do a bunch of, deep reading and have you guys watching me staring at this, 6502 block diagram for an hour on end. Cycle test. We're down to 3 failed tests. Sweet. Pull the processor status register. Now that's odd. Okay, this does say PLP is 4 cycles. So let's think about this. So it's a single byte instruction. So we're pulling the opcode. And then what? Oh, and then and then we're doing a stack read. We're reading a byte off the stack. Okay, so that's 2. And then we're modifying the stack pointer, and that's 3. So I don't know where the extra cycle pops in. If you happen to know what the 6502 is doing that's causing it to burn an extra cycle in a PLP, put it in the comments. So here, let's see. Let me look at my pop byte logics to make sure I understand here. Okay, so we're doing calculating the new stack pointer, we're reading the byte, we're doing increment cycles. Oh, we're already, wait, why are we doing an extra increment cycle there? That probably actually really belongs here. We're gonna modify the stack pointer, and then that's a cycle. And then we're gonna read a byte, and that's a cycle. And then I don't know what we're doing past that. So okay, that's fine. And let's go ahead and just stick that extra cycle in here, and we're going to say to do where should this extra cycle actually go? Okay, now I've got a couple of weird ones here, like SBC indirect comma Y. This feels like it's the test is wrong. I did use AI to generate most of the test entries. Okay, so this is a 2-byte instruction, so we've got SBC indirect comma y. Whoa, come back here. Okay. Indirect comma y. It's 5 cycles unless we cross a page boundary, in which case it'll be 6. And in this case, this is no page cross. So indeed, it should have been 5 cycles, but we took 6. Okay, so the test is not wrong, but maybe the test data is wrong. So let's actually pop over to the test data and just verify that. Okay, oh, so here, in 0 and 1, in our 0 page, I've got the value 0. The effective address is 103. That doesn't sound right. Yeah, let's see what we got going on in the test program. So So this is going to read the values from 0 and 1 and then index by y. In this case, y is AXY. Y is FF. So apparently I have the values. This is no page cross. Now I wonder if these need to be set to 0. So this is the MMU interface, or memory management unit. So this is a module that acts like all the rest of the Apple II outside of the CPU. And actually, in this case, in the test harness, it doesn't emulate any of the I/O or ROM or any of that. It's just basically 6502 connected to 64 kilobytes of RAM. For testing, that just makes things real easy. Okay, so I'm going to try this again, having specifically set those variables, because they may not be getting cleared anywhere, and I may have started with bogus information in it. Oh. Oh. I bet I know what it is. All right. We do have 2 failed tests. That's fine. So actually, I guess it was just not 0 like I thought it was. That's fine. So for testing the things that cross page boundaries, I set up addresses 2 and 3. Actually, to be correct, I can add these here with an address 10FF. So if I add anything to that, right, it's going to cross the page boundary. And that's how I test like the, indirect comma y off of 2. If I go up here to some tests here, let's see, LDA indirect. Indirect comma y. Right. So you'll see here, I'm doing LDA indirect comma y from address 0. So we know now that's 0. So that's going to not cross the page boundary no matter what. When we test it here, we're doing, LDA from 0x02 indirect y, and we're setting the registers to be FF going into it. So we're definitely going to page wrap there, FF plus FF. In fact, if I go here and say LDA indirect comma Y with crossing. You'll see here we have an effective address of 11FE. Interestingly here, I think some of my test instructions must write to address 0. And so, in fact, let's just look at the increment addresses here. Yeah, okay, there we go. Increment 0 page. So while I'm setting it, to 0 here, it's outside this loop that's going through all of the test instructions. So really what I ought to do is put this in here so we're resetting those memory locations every time through. So let's do that. Okay, that makes sense now. So we've got increment 0, 0, blah, blah, blah. Okay. Okay, I have 2 failed tests left. STA, absolute comma Y. STA is an absolute Y. I've met STA. Man, absolutely a Y. Okay. Absolute comma Y should be 5 cycles. And we're only taking 4. That's weird. We've got opcode, operand, operand. That's 3 cycles already. We've got the store, and then we've got to add Y. So I'm definitely a cycle short. Okay. Okay, store operand absolute comma Y. This is only used in that one instruction. Okay, read word, so that's 1, 2, 3. Oh, this is that same thing that we dealt with the X, where I bet we need to add a cycle every time. Okay. Let's just call that absolute Y comma right, and then here. Da, da, da. Are there no other places where we store absolute comma Y? That doesn't seem right. Those are fake instructions. Go away. Add and compare exclusive or LDA, LDX, ORA, SBC, STA. Oh, well, STA is in fact the only instruction like that. So I made, yeah, that's right, I made that change. Okay. Oh, bad code. What is going on here? What have I done? Okay, let's go back and follow that. I bet a bunch of you are already screaming at the screen going, you did the thing wrong. Okay, store operand absolute y. Oh, I didn't actually. Oh, did I make. Yeah. I did the wrong thing here. I don't need to do that. In fact, since this is actually the only instruction that does this, I can just put the extra cycle. So I've got a few of those to follow up on. The last thing I would expect would be we're writing the byte. So we get the address absolute comma y. One failed test left. All right. And that's STA indirect comma y. I'm doing 5 cycles and it should be 6. So let's see. STA indirect comma y should always be 6 cycles. Okay. And again, here, this is only used on this one instruction. Thank you, AI, for adding the to do automatically. Okay. Oh, I think there's actually an instruction I need to add, and I wanted to show you guys how I was doing it. No failures. Look at that. Nice. Okay. Well, now all the instructions I'm testing execute in the correct number of clock cycles. So that's a plus. We still have a couple things to deal with. Obviously, we need to do the just check those things and make sure that those cycle counts shouldn't be somewhere else. But I also need to add an instruction. So let's go up here and see which one I forgot to put back in. Okay, so we've got ADC, we've got AND, we've got ASL, we've got BCC, BCS, BEQ, bit. Okay, branch of minus, BNE, BPL, break. BVC, BVS. Okay, CLC, those. Pair. CPX, CPY, DEC, DEX, DEY, EOR, INC, INX, INY, jump indirect, JSR, LDA, LDX, LDY. Maybe I don't. Let's see, LDY. Oh, yeah, it's right here. After LDY comes LSR. So here's how I was doing this, right? I've got enough examples of doing the things I want in my code already that I can just come in here, copy this, and say debug tests for this instruction. Now, this is just copying and pasting from the 6502 instruction manual on mass work, and it's got the cycle counts and everything. So I'm not, I'm providing all the information, and it's got examples of how I want this stuff structured already. So that's all I have to tell it, because it's got the opcode in here and the number of cycles, and then boom. If you guys haven't been coding with any of the AI assistants, like this is Cursor editor, it's integrated editor and AI assistant. It's amazing. So this converted that text from here into my test structures, just like that. It's pretty amazing. This is not an AI video, but this makes me super extra productive, right? I might have been a 5x before, but now I'm a 15x, if you know what that terminology means. It's great. Anyway, so there we go. And I'll just double check a couple of these. Okay, so it's 4A, 46, 56, 4E, 5E. So that's 1, 2, 3, 4, 5 and 5 variations. Yeah, that looks right. Okay. I'm going to accept it. All right, and let's build. And I can just do grep LSR here. Oh, man. That's painful. Okay, so this is good, right? This is why we do this stuff. I've got one more bug to fix. The great thing about this was a lot of work to set up, right? This has been, even with the AI help, like 3 hours invested into this. But every time I touch the CPU code, I can just run this again and make sure I didn't break something. And that is invaluable. Okay, LSR ABS, X. Logical shift right address. What's going on here? Okay, so let me think about that. So LSR, X, it should be 7 cycles. Okay, that's a lot going on. So we've got opcode, operand. That's 3. We got to add the X. That's 4. We've got to load from memory. 5, shift, right. So that's our 7 cycles. Get operand address absolute, X. This feels like what we were just playing with. Yeah. That's a read, modify, write instruction. So I need to do this. Oop. Okay. Sweet. All the LSRs pass. And I have no failed tests. So now that I've just been building the test, Actually, in the background, I've also been building GSSquared. This builds the whole suite. I've been just making changes here to either the test program or the CPU code. One of my targets here has been GSSquared. So that's the other thing that's nice about this setup, right? Is it's a little standalone program, but it leverages these libraries that I wrote as part of GSSquared. So the CPU is set up as a library, and I can just pull the CPU into other little programs. So if I want to emulate a 6502 in any other code base for some other reason, I can do that. Like in this test program, or, let's say I wanted to emulate a Commodore disk drive for some reason, right? I could just stick an extra 6502 in that device. What else uses a 6502 as a subsystem? Maybe the, I don't know. Does the Unidisk or the Apple 3.5 drive have a 6502 on board? Let me know in the comments. So, and that it's really easy to set up right here. So this is just my main function of my test routine. It's literally just create the MMU, tell it this is doing a memory map of the pages in there. I'm just pointing it to a big block of memory here. I'm creating a CPU instance and setting the minimal stuff I need, and that's it. And then I can execute, down here. Test instruction. Here I execute one instruction. This right here does one instruction execution and then returns. And that is how I integrate that into here. So, if you're interested, you can go pull the GSSquared code and you can play around with this yourself. You can make your own little emulated 6502 single board computer if you want. Go have some fun with it. I'll see you next time. Like and subscribe. You liked it. Well, I liked it. All right. Bye.